So, last class I have discussed that how we can determine the allowable bearing capacity of foundation based on SPT value if the foundation is resting on sand. So, today I will discuss that how we can design the foundation on the clay soil. So, before I go to that clay soil design part, so I want to determine that I will to give an idea that how we can use the dimension for a particular combined foundation, because most of the cases we have discussed the isolated footing. So, now as you know that if the influence zones are crossing each other, or that means they are touching each other for a particular or for the foundations, if the foundations are very close to each other, then we can go for a combined foundation. For example, these upper three footings are the isolated footings, and then this is also isolated footing. So, now this is the combined footing where two footings are two columns are given one particular foundation. So, this is combined foundation and this is also combined foundation. So, we can go for different shapes of combined foundation. This is rectangle, this is trapezoidal. So, now I will discuss that how we can determine the dimension of a particular combined foundation. So, this is a particular combined foundation which is a rectangle. So, which is more or less symmetric type of foundation. So, that means these columns are located more or less by the equal distance from the edge. Okay. So, but here sometimes it is a case where the one edge and the column are in the same line. So, this is the case, okay, where the one column and the edge of the foundation in same line, but the another column is with a certain distance from the edge of the foundation. So, this is the total foundation width or length, you can say. So, this is the foundation length and there is a width in the perpendicular direction. So, there is a W or W 1 and W 2, because this W 1 and W 2 may be different, okay, and which is acting on the column. And so, we have to determine the dimension of this foundation, combined foundation. Okay. So, here the allowable soil pressure or bearing pressure is given, which is 80 kilonewton per meter square, and I have already discussed in my previous class how we can determine the allowable bearing pressure. So, here that allowable bearing pressure or Q allowable, which is given 80 kilonewton per meter square. Okay. So, one foundation is carrying 500 kilonewton, another foundation or another column, I should say the one column is carrying 500 kilonewton, another column is carrying 1000 kilonewton. Okay. So, now we have to calculate what is the centroid of the point of application of this resultant load. So, that means W 1 and W 2 load is acting. So, what is the point of application of the resultant load? Okay. So, for that purpose we have to take the moment of these loads from one particular column. So, we are taking the moment from this H column center with the load. So, that load is say is acting here. So, that is W, or here I should write that the resultant force Q 1 plus Q 2 is acting, okay, and that is equal to say x bar from the centroid or the center of the H column say. Okay. So, here also it is the center of the H column, this is x bar, but it is the this plan is not this foundation. Okay. This plan is for this foundation, this upper foundation. This plan will be different, where this will be probable plan for this particular foundation. Okay. So, this term will not be there. Okay. So, this term will not be there. So, the probable foundation plan for this particular case combined footing will be the without hatch portion. Okay. So, now I can say that x bar, if I take the moment. So, x bar into q 1 plus q 2, that is will be equal to 1000 into 4.5, because it is a 4.5 meter distance. The distance between the two column is 4.5 meter. So, the x bar will be equal to 1000 into 4.5 and W 1 plus W 2 will be 1500. So, this is 1500. So, this is equal to 3 meter. So, the x bar is 3 meter. Now, what is the area? Area of the foundation. So, area of the foundation is total, or required area of the foundation is the total force is coming 1500 kilonewton, or for total weight is coming 1500 kilonewton, and your allowable bearing capacity is 80. Okay. So, that is your required area of foundation, and that is 18.75 meter square, because here no factor of safety is required to apply, because allowable bearing pressure is directly given. It is not the ultimate bearing pressure. That means, settlement and bearing both the cases are considered. It is allowable bearing pressure. Okay. So, that means, settlement and bearing both are considered, minimum one is given as a allowable bearing pressure. Because last class I have discussed that you can go separately and provide the minimum one, and there is a correlation is also available, where directly you can get the allowable bearing pressure. But the last previous case we saw that the settlement consideration is giving the minimum value or the lowest value. That is why you provided that. So, here that value is directly given. So, that is why that means if we multiply the allowable bearing pressure with the area, that load should be equal to the load that is coming to your foundation. So, here that based on that we determine the required area, and that is 18.75 meter square. So, my L value will be how much, because this is the center as where the your this x bar distance is the distance where this resultant loads or forces are acting, and if we consider this is as the center of this foundation, okay, then my required L will be 3 meter is that distance plus 0.3 meter. Okay, plus point, or you can say that this is the edge and this distance is 3 cos 3 meter. Okay, this dimension of the column is 3 cross 3 meter, and from the center we have taken the moment. So, we can write. So, this will be our 0.3 divided by 2, your 0.15 meter. Okay. So, from this edge up to this center, this distance will be 3 plus 0.15 into 2, because that will be total, because we are taking this is the center of this foundation. So, this will be 2 into 3.15. So, this will be 6.3 meter. Okay. So, this will be 6.3 meter. So, the required length we have decided. So, that is 6.3 meter. So, L is 6.3 meter. So, the B will be A divided by L. So, A is 18.75 and the L is 6.3. So, the required B is 3 meter. So, the dimension of this foundation is final dimension of this foundation is 3 meter cross, you can provide, if I provide in round figure. So, I can provide it 6.5 meter. So, this will be the probable dimension of this foundation. You can provide 6.3 also, because that is the minimum requirement. So, I am providing the 6.5 or 3 cross 6.5 meter square your, or 3 meters square 6.5 meter dimension of this foundation. So, this way we can determine the dimension of the combined footing also, if the allowable bearing pressure is given. Now, the next problem that I will discuss is the design of foundation on the clay soil. So, here this is the example problem. So, we have 16 column. Okay. So, next problem we have 16 columns in a particular building, say, and the spacing between the column is 4 meter. This spacing is also 4 meter in the both directions, and the load which is coming to the outer column is 500 kilonewton and inner column is 600 kilonewton. So, all 4 inner columns the load is coming 600 kilonewton and all outer column load is coming 500 kilonewton. So, initially we have to check it for the foundation for every column. If the isolated footing is fine, then we can provide isolated footing, provided all the settlement criterias, I mean the differential settlement or the torsion or rotation or the your maximum settlement or criteria are satisfied. But in this case, it is observed that these individual or isolated footing we cannot provide for this type of soil this type of soil and for this type of loading condition, because your footings are overlapping each other or maybe some differential settlement issues are there. So, we have to provide a combined foundation for all the columns, and that means we will provide a raft foundation. So, I will discuss about the design of raft on the clay. On clay. Okay. So, the total width. So, that raft. So, for the initial trial we will consider a length. So, length or B it will be same, because it is a square pattern of building. So, your length of the raft or width of the raft will be. So, we are taking the minimum width will be that. So, this column dimensions are also given. So, this column dimensions are given your 0.4 cross 0.4 meter square. Okay. So, the minimum dimensions will be, this is 4 meter, 4 meter, 4 meter. So, this will be 3 into 4 meter, okay. And then both side is 0.4 by 2 plus 0.4 by 2. So, it will be, so 12.4 is the minimum dimension that we have to provide. But for first trial, if you provide just edge of the your columns, the edge of the foundations. So, rather than you provide some distance beyond the edge of the foundations also, beyond the edge of the column also, because in previous case we provided the column as the edge of the foundation, that is the special case, some restrictions are there. Otherwise, we provide some distance from the edge of the column also, but here also we provide some distance from the edge of the column. So, 12 meter is the minimum distance that we have to provide, and then I have decided to provide 1 meter extra in both the sides from the edge of the or from the center of the edge column. Okay. So, that means from the center of the edge column 1 meter addition this side and 1 meter this side. Okay. So, our dimension, minimum dimension that we are giving for the first trial is 14 meter, and obviously L will be also 14 meter because it is square shape building. And for the first trial, now we will go for the net stress that is acting on the raft. The total stress, the total amount of load is 600 into 4, 600 into 4 column, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 12 column the load is 500 kilonewton. So, the total load is this much, and then the area which is 14 cross 14. So, Q net is 58.3 kilonewton per meter square. So, the net stress which is acting on the foundation is 58.3 kilonewton. Now, the soil profile. Okay. So, this is the ground surface, and we have a soil profile which is 3 layer soil. Three layer soil, and there is a rigid layer below the third layer. So, this is the third layer, this is second layer, and this is first layer. And the properties of the first layer is given. The unit weight is 18 kilonewton per meter cube. Then Cu value undrained cohesion is 60 kilonewton per meter square. Then Cc 1 plus E0 is 0.08 for the first layer, and Es value, elastic modulus. So, Es value I have given the range, E value with the Cu undrained cohesion. So, from that given range roughly we are taking 700 Cu as the Es or Eu. So, 700 Cu will be your 42,000 kilonewton per meter square. For the second layer, unit weight is 19 kilonewton meter cube, undrained cohesion is 70 kilonewton per meter square, Cc 1 plus E0 is 0.06 and Es is given 49,000 kilonewton per meter square. For third layer, unit weight is again 19 kilonewton per meter cube, undrained cohesion is 80 kilonewton per meter square, Cc 1 plus E0 is 0.04 and Es is 56,000 kilonewton per meter square. Okay. So, this is the soil property, and water table is located at a depth of 1.5 meter from the ground surface, and the thickness of each layer, this is 0 meter, this is minus 5 meter, this is minus 18 meter and this is minus 30 meter. So, this the depth of the soil layer is up to 30 meter. After that it is the rigid layer and the thickness of the first layer is 5 meter, second layer is 13 meter and third layer is 12 meter and all the properties are given. So, these properties are basically the lab properties, because C c plus 1 plus E 0 these are determined from the consolidation test, then C u and unit weight. So, because these you can use different correlations of the field test data and then you can determine the C u values also, but most of these data are tested in the lab and then these data are used. So, that means these data we obtain from the laboratory test. So, that means here these are the data which is given and this E s we have used these correlations and then we got this E s with respect to the cohesion value. Now, E s also we can determine in laboratory if we have the undisturbed soil sample and you will get the elastic modulus, that also we can determine, but here that data was not given. So, that is why you have used the suggested correlation and that is within the range you have taken 700 Cu. So, E u is 700 Cu, that we have used here. Now, this is the your soil data. Now, these are the loading condition and we have decided we will go for the raft foundation. Now, for the first trial we are putting our raft as a depth of 1.5 meter. Okay? Where the position of the water table. So, this is the position of the raft. So, the df depth of foundation is 1.5. Then we will go for the first trial. Another property is given, the unit of weight of water is also given 10 kilonewton per meter cube. Okay. So, these are the properties are given and we have placed the foundation at 1.5 meter below the ground surface, because these up to 5 meter the water soil properties is same. So, we have placed it here. Suppose if in the shallow depth you have a very soft soil or the poor soil, then you can place slightly in greater depth also, so that you can place the foundation on a better soil, but here the soil properties is same. So, we are putting it on the 1.5 meter below the ground surface. Okay. So, now we have to go for the two checks, one is for bearing capacity, another is the settlement. So, first we are going for bearing capacity check. Okay. So, as I have mentioned during my bearing capacity discussion for shallow foundation, that it is better to use two bearing capacity equations. So, here it is only clay. So, I have decided I will go for Skempton bearing capacity equation, which is applicable for only clay, because here all the layers are the clayey soil, and then I will use the Henson bearing capacity equation and then we will decide that which value we will use. So, first we will use the Skempton. (1951) and that bearing capacity equation is net ultimate bearing capacity is Cu N c. Okay. And for square footing, this is because it is a square footing, square foundation, N c is equal to 6 1 plus 0.2 df by b, and that is equal to 6 1 plus 0.2 df is 1.5, b is 14 and that is equal to 6.13, which is not greater than 9 because they should not be greater than 9. So, we can use 6.13. So, NC value we got, that is 6.13. Now, what is the CU value? Because as I mentioned in my previous example problem, that for bearing our influence zone is B. Okay? And for settlement it is twice B. So, B is 14 meter. So, for bearing influence zone will be your 14 plus 15 point up to this 15.5 from the ground surface. So, for the bearing influence zone will be up to this, which is 15.5 meter, 14 meter from the base of the foundation. So, up to 15.5 meter will be the influence zone for the bearing, and for the settlement it will be 28 meter plus 1.5 meter. So, 29.5 meter up to here, say 29.5 meter. Okay. So, now the question is which you will consider, because it is on the first layer, it is on the second layer also. Okay, in the first layer Cu value is 60 kilonewton per meter square, where the first layer is 3.5, but the maximum part is on second layer, because 3.5 is on first layer out of 14 and around 9.5 is in the second layer. So, the majority part in the second layer. So, and second layer Cu is 70 kilonewton per meter square. So, now what to do? So, if suppose your difference of the Cu is very high, then we can go for the lowest Cu value for our design to be in the safe side. But here difference is not that high, significant. You can see it is 60 kilonewton per meter square, then 70, then 80 kilonewton per meter square. So, that means here we will take the weighted average value. And another thing I want to mention, that I have discussed that you can determine the bearing capacity for layered soil also, but that theory is applicable that if you have a very strong lower soil and very soft upper soil, or very weak upper soil or strong lower soil, or reverse, that means very weaker bottom soil and the stronger upper soil. Okay, so, that means the variation of Cu value is significantly high. Suppose the one soil as a top soil is very strong and bottom soil is very soft, or bottom soil is a softer soil compared to the upper soil. So, that means there is a difference of Cu value. In such case, you can use that theory also and determine the bearing capacity of the foundation in layered soil case. But here that theory may not be applicable here, because here the difference is not that significant. Okay. So, you can see that the theory that I have discussed is for 2 layer soil. Even for this 3 layer system also you can convert it to 2 layer system. That is not a problem, because if your suppose your bottom layers are very soft layer, then you can take the weighted average for the bottom layer and make one bottom layers as the soft layers, and the stronger layers you can take the weighted average and make it 2 layers. So, in the stronger layers in the top and the bottom layers are the softer layers. In such case, you can take the weighted average and make one strong bottom layer and top layer and one soft bottom layer, and then you can use that theory that I have discussed for layered soil, or vice versa. That means, that is I have discussed also how you can use if is a softer top layer and the stronger bottom layer also. That theory also I have discussed. So, both the cases you can do. But in such case your soil has to be some, one is stronger portion, one is very softer portion like this. But here it is not the case, it is more or less the same Cu value, you can see 60 to 80 it is varying. In example problem I solved 40 to 100. Okay. Or sometime it can be 21 Cu value is 20 for one layer, another layer is 100. That case you can use that the theory which is proposed, or some layers the range of Cu value in the bottom is say 20 to 40 and the upper layer is say 100, around 100, then that case you can use. Or in opposite is some layer in the top it is 20 to 40 something like that, and bottom layer is steep, so 100, 120. In that case you can use the layered soil theory, but in this case it is more or less same. So, that is why we will take our conventional bearing capacity theory by taking the weighted average of the Cu value. So, that weighted average we will take. So, this is this layer you can see this is 3.5, okay, and this one will be 9.5 or 3.5 and this will be 10.5 because this is total is 14. So, this will be 10.5. So, we can see that Cu value will be 60 for the top layer, then 3.5 for the top layer, then thickness, then the bottom layer is 70 into 10.5, total is 14. So, this is 14. So, Cu value is 67.5 kilonewton per meter square. So, one thing you can do, you can directly use the 60 to be in the safe side, 60 kilonewton per meter square, but as your 10.5 meter most of the part is in the second layer. So, that is why I have taken the weighted average value. So, 67.5. So, Q net ultimate is 67.5 into 6.13. So, that is 414 kilonewton per meter square. So, this is as per scheme 10. Now, I will use the Henson's bearing capacity equation. So, if I go for the Henson's bearing capacity equation. Now, for phi equal to 0 degree, because here phi equal to 0, that Q ultimate is equal to Q ultimate is equal to Cu NC, then 1 plus SC plus DC minus IC, then plus Q. But here the inclination effect is not there, because loading is not inclined, it is perfectly vertical. So, that is why the modified equation will be Cu NC 1 plus SC plus DC plus Q. So, IC will not consider, because add inclination is not present here. So, my Q net ultimate, because this is ultimate. So, net ultimate will be Cu NC 1 plus SC plus DC. Okay, so, Q net ultimate, that means minus Q, we have taken the net ultimate. So, from the chart we can see the NC value for phi equal to 0 is 5.14 for phi equal to 0, and SC, the shape factor is 0.2 B by L. So, this is 0.2 into 1 equal to 0.2. Now, depth factor DC is 0.4 dF by B, because as dF by B is equal to 1.5 divided by 14. So, it is less than 1. So, we have to use this correlation. So, that is 0.4, dF is 1.5, B is 14. So, this is 0.043. So, Q net ultimate at for Henson is 67.5, that is the weighted Cu, NC is 5.14, then 1 plus SC and DC 0.043. Okay. So, this is 431 kilonewton per meter square. So, we have used two bearing capacity equations, one is Skempton and is Henson, and Skempton is given 414 kilonewton per meter square and Henson is given 431 kilonewton per meter square. So, I am using the lower value of these two. So, that Q net ultimate that we are using 414 kilonewton per meter square. So, factor of safety that we are getting is our net ultimate bearing capacity is 414 and the load which is acting is 58.3, that is the net stress which is acting on the foundation. So, this is 58.3. So, this value is 7.1, which is much more than the 2.5. So, this is as per the bearing it is over safe. So, we have done the checking for bearing only and as per this checking it is over safe. So, now we have one checking we have to do, that is for settlement. Okay. So, we have done the one part, that is the bearing capacity, and that part it is safe and it is over safe. But let us see, we will do the bearing capacity check and let us see what is the then we will do the settlement check and let us see what is the settlement value for this particular raft foundation on this particular soil strata. Then based on these two consideration, we will decide what will be the final dimension we will provide. So, in the next class, I will do the settlement calculation for this particular foundation and then we will decide what would be the actual dimension of the foundation. Thank you.